Okay, now we are gonna start with some exercises. Here they are giving us a three-phase inductor motor drawing 60 amps. Okay, and they're asking us the air gap power, the electromechanical power, the output power, and the efficiency of the motor. So first, we can figure out the power that is in the motor, that is going in. And we know that this is the square root of the total voltage times the current in the line times cosine of the angle. And we know that the cosine of the angle between the current and the voltage, or the voltage and the current, is our power factor. So we know that our P is square root 3, 480. Our current is 60 amps. And our power factor is 0.85. And like that we have 42.4 kilowatt. Okay, now in a previous video we figured out the power flow in a motor. So we said that here we're gonna have the power in, then we are gonna have the stator copper losses, then what else we lost the stator is gonna be the core loss. So after we have these two losses, we get our air gap power. So the power that is going into the rotor. And so we are gonna have the rotor copper loss. And then after the copper loss, we are gonna have our mechanical losses, windage, friction, and finally, whatever is left is the power that is going into the shaft. Okay, so we are gonna follow this flow to answer these questions. So the air gap power, so the air gap power here is the power in minus the stator copper loss minus the core loss. So we have figured out that our power in, well, and this is gonna give us our air gap power. So our air gap power is gonna be our 42.4 kilowatts minus our stator copper loss. Here is given 2 kilowatts minus our rotor copper, our core loss, and our core loss is an 1800 watts. So for part A, our power in the air gap is gonna be equals to 38.6 kilowatts. Okay. For B, they are asking us the electromechanical power converted. So the electromechanical power, PEM, is what we get after we have the power that is going into the rotor. We have the rotor copper loss, so what is left is our electromechanical power. So it's gonna be our air gap power minus our rotor copper loss. So power in the air gap minus our power in the rotor copper loss. Okay, so our electromechanical power is going to be 338.6 kilowatts minus how much are we losing in the rotor? 700. So like this we get 38.6 kilowatts minus 700, that's 37.9 kilowatts of electromechanical power. And finally, we got the power out. That's what they are asking us. The output power, that is our power in the shaft, is equals to our electromechanical power minus our mechanical losses. We said here that friction and windage losses are 600. So aquí, I'm just gonna say mechanical losses. So our power in shaft is gonna be equals to 37.9 minus 600 watts. This is kilowatts. And this is equals to 37.3 kilowatts. And finally, they are asking us for the efficiency. And the efficiency is the power out over the power in. So the power out is 37.3 and the power kilowatts, and the power in is 42.4 kilowatts, and we multiply by 100, and that's going to give us a percentage of 88%. Okay, so if we follow if we are giving the power, the losses in power, we can calculate it easily following the power flow. Now we are gonna work with synchronous speed and rotor speed. So the first thing that they're asking us for this exercise is to get the synchronous speed. So the synchronous speed in RPM is ns equals to 120 times the frequency over the number of volts. So here we have 120, a frequency of 60 hertz, and it's telling us that it's a 4-pole machine, so 4. So we get 1800 RPM. 1800 RPM, yes. Now for B, what is the rotor speed of this motor at the rated load? Okay, so it's connected as a full load slip of 5%. So a full load, we have a slip of 5%. And we know that our slip is going to be our synchronous speed minus our electrical over our synchronous. So our synchronous speed minus our rotor speed, not our electrical, rotor speed. This is the rotor speed. So we can say that our rotor speed is equals to minus our slip times our synchronous speed plus our synchronous speed. So in R, because I want to write it in RPM, is going to be minus 0.05 slip, and we have our synchronous speed of 1800 plus 1800. I could have factored this out to make it prettier, but I'm just gonna write it like this for now. So this is gonna be equals to 1710 RP. Okay. Now for C, they are asking us what is the rotor frequency of this motor at the rated load. So the rotor frequency is gonna be the frequency times the omega r. It's gonna be the frequency times the slip. So omega r is gonna be equals to 60 times the slip. That is 5%. 60 times 0.05. I'm sorry about this here. The sound is my WhatsApp. I'm sorry about that. So this is gonna give us 3 hertz. Now we are gonna continue with D. We have here what is the shaft torque of this motor at the rated load. Okay, so we have here the rated load in horse power, so 10 horsepower. And now to go from watts to horsepower, we divide by 746. So to get the power in watts, we get, well, we have the 10 times 746, and this is going to be in watts. So our power is going to be around 7,000 kilowatts. Okay, now in the previous video we figured out that the developed torque is equals to the power over the speed in mechanical, synchronous speed in mechanical in the of the rotor. So we are gonna have this is equals to the power we have in R 2 pi over 60. So we are gonna have 700 for 60 over what we calculated before for our speed in the rotor. That is 1710. Now we multiply times 2 pi over 60 because we need this in hertz, and right now this is in RPM, and this is gonna give us a developed torque of 41.66 newtons per meter. Okay, to the next one. They are asking us to calculate voltage space phasor as a function of time. Okay, so we have 3 phases. Okay, we have done the voltage space phasor a lot of times. So by now we know that the RBS, or the phasor in alpha beta, is gonna be equals to 3 halves Bm cos of omega t minus J sine omega t. Okay. Also, what can we say from here? We have, they are giving us LS, LR, RR. Okay. So we are gonna say for this motor, we are gonna say that L1 is equals to LIS minus L naught. So this is equals to 0.0553 minus 0.0538. So this is gonna give us 1.5 millihenry, and we're gonna say that L2 is equals to LIR minus L naught. Now we decide this because L naught should be our magnetizing inductance, so this one should be bigger than L1 and L2. That should be our leakage, or where. That's how I understand it. If somebody in the video, if somebody sees the video and know the actual reason, please let me know. So for L2, we are gonna have 2.2 millihenries. Okay. So now for A, we are gonna have 3 halves that are BS is equals to 3 halves. Our maximum, that is, and they're telling us that in RMS. So we will have our 163, and this is in RMS. And this is in RMS, so and we have cos omega t. In this case, we have 60 hertz, so we have 120 pi t minus, so this is our alpha component, j sine, no j, 3 halves 163 sine omega t 120 t. So we can factor out our 3 halves 163, and it's gonna give us cos or 100 pi t minus j sine 100 pi t. So this is just e to the j omega t 100 pi t. Okay, so this is our BS in RMS. So this, if we multiply these two, we have 3 halves times 163. So our BS is gonna be 244.5. e to the j is 120 pi t. Okay, so this is our space phasor as a function of time. Now we are gonna do B. They are asking us to do find the three-phase stator currents as a function of time when the rotor is locked. Okay, so when we did our squirrel cage model over here, let's take this one. Here we have that our slip is R2 over S. Our slip is the percentage that we have omega S minus omega R over omega S. So if the rotor is locked, that means that these two, if the rotor is locked, this means that we have an slip of 1 of 100%. So if our rotor is locked, we have our S equals to 1. Okay, so that's what it means to have our rotor locked. And now we have here our IS. We know that we have here our IR. This is our R1. This is 2.77. This inductance is 1.5 millihenries. This one is 0.0538. This one is 2.2 millihenries. Okay, and we have an R2 of 0.183. So this is our circuit when our rotor is locked. So they are asking us to find an expression for our three-phase currents. So we need to find IS, and to find IS, we're gonna call these two S1 equivalent, S1. I'm gonna call these two X2, and this is X0. So we know that current is voltage over resistance, so we first need to find our total resistance or total impedance. That is going to be 1 over x1 plus x2 times s0 over x2 plus x0. This is going to give us our total equivalent impedance. Now to do this, I just well, first we need to transform each of these into impedance. The inductance. So we multiply by j omega times the inductance to get the x. And to do these calculations, you use MATLAB. Uh, over here to calculate xt. So here are the reluctance and the equations that I said that I was going to put. So R1 plus S1 is one equivalent, X2, R2 plus S2 is the other equivalent. And like this we can find our total impedance. And to find X1 we multiply by omega. And we know that omega is 120 pi. So when we plug these numbers in our calculations, we're just gonna get that we have 0.445 plus 1.3637J for our total. And we know that our IS is gonna be equals to our BS over RT XT. And we have our BS that we calculated over here. And remember, this is in a steady state, so we don't change with time, we just have the magnitude and the angle. So this is gonna be 244.5 angle of 120 pi in radians over what we just calculated here. Okay, so and now we are gonna divide this over square root 2 because we don't want it in RMS. So this is gonna be as 120.4 minus 1 in an angle of minus 1.6 in radians. So this is voltage peak. So now we have our magnitude and our angle. So we can figure out our current. It's gonna be IS equals to, oh well, I remember here I think I confused the terms. Here we change it to RMS again. because we had it in RMS. Yes, so okay, let's keep going. 120.4, that is our magnitude. If we want it in RMS, we have to multiply by square root 2 because we just changed it here into no RMS to peak value. And we're gonna have our cos of 120 pi t minus our angle 120.6 radian plus j sine 120 pi t minus our angle. Now this is our alpha component and our beta component is the same that we did with the voltage, just that in the equation we subtract an angle. So our IS in RMS is equals to 170 EJ J 120 pi minus 1.26. So this is our current in our alpha beta. Now if we want our currents normal currents, we know that when we go from our three phases we multiply by 3 halves, so here we're going to multiply by 2/3, so we're going to have 170 cos of omega t minus our angle. That's for A. For B, it's gonna be, well, this multiplication, that is 113.3 cos 120 pi omega pi t minus the 120 shift minus our angle. And similarly for C, it's the same. There's a magnitude here, but when we do the cos of omega t, we subtract 4 pi by 3 for our 240 degrees shift, and we have minus 1.6. Okay, so that's what we get our 3 currents, and these are our 3 currents, and this is our alpha beta component. So 3 phases stator current as a function of time, and our expression for stator current space phasor as a function of time. Okay, so our IS is our space phasor. Okay, now find the 3 phase rotor currents as a function of time, so the same but with our IR. So here we have this circuit where we have our IS and IR. So to find IR, we can do a loop. It's gonna be equals to x minus, if we go from here, minus s naught, that's gonna have IS plus IR here, because IS is coming here, IR coming here, so they add when they go through S naught. And this is gonna be minus IR multiplying our x2. Oh, remember, we are calling x2 the sum of R2 and this R2. So if we expand this as minus x naught IR minus IR is 2, and we factor our IR, S3 plus S2, so IR is equals to minus S3 over S3 plus S2, times is. So this is how we can find our IR. Okay, I don't know. It's copying but not copying everything. Well, okay, this is our IR. This doesn't want me to move it. I don't know why. Okay, so what I did, I just plugged this in MATLAB again. So IR, we have IS, I naught, R2, and X2. So this is just the formula that we figure out, minus IS, X naught over X naught plus R2 plus X2. I just did it like this because it's, if we change the values, we can keep working with different exercises. So just to have it down here, we have IR equals to minus X3. What we are calling our X3, where X3 plus X2 is. And when we plug those values in MATLAB, we get 163.7 e to the j 100 pi t plus 1.9. So from this, we get a magnitude that is 163.7 and an angle that in this case was 1.9. So when we put in a form of a phasor, space phasor, we can write it like this: our magnitude omega t plus plus our angle. And just like we did with our other example, our IR, our current in the phase A of the rotor, is gonna be 2/3, what we just figured out here, 166.7 cos of omega t. This is 120. I keep thinking in 20 hertz, so in 50 hertz, so that's why I keep writing in 100. But here we're working with 60, so this is 120 pi t plus our angle. And for our current in B is gonna be, for this multiplication, that is this, cos omega t minus our 120 shift plus our new angle. And ICR is the same magnitude, cos of omega t, 240 shift plus our new angle. So like that we can find our currents in our rotor, in our stator, in both space phasor and when we want it as a function of time in our three phase. Okay, so for the next one, here, for the last exercise, we said that we have a rotor speed of 125 radians per second. Find the slip and a steady state torque. Okay. So we know that our synchronous speed is 120 frequency over the number of poles. So we have 120 times 60 hertz over 4 poles. This gives us 1800 RPM. And now our frequency, our speed in our rotor, they are saying that is 185. So we turn this into RPM. It's in radians per second, so we turn it in RPM. So it's gonna be 76.6 RPM. Now that we have both our speeds, we can figure out that it's our synchronous minus our rotor over our synchronous times 100. This is gonna be our slip. So we have 1800 minus 66.6 over 1800 times 100. So we have a slip of 1.8%. And before we figured out that our steady state torque is given by this formula. So if we plug the values, we have IR, we have, remember we have IR in RMS because the formula was in RMS. We have our R2, we have our S, we have our synchronous in mechanical. So for this case, we have our circuit, but this time we have here our sleeping. Oh well, we don't actually have a yet because this was for a sleep of 1, but now we have a sleep of 0.018. So we need to do the same that we did over here, all of this to figure out IR, to figure out IS, but this time with an R2 of R2 over S. So because I was doing this in MATLAB, I can just change the sleep value from 1 to the one they are giving us there and get our developed torque of 83. So I know that this looks a little bit like cheating, but it is just because I have these, it's the same formulas, just change the sleep. Okay, and they are asking us to plot the steady state torque versus a sleep curve in MATLAB. Okay, so here I have here MATLAB. So I was doing everything in MATLAB because I knew the exercise was going to ask us this. So they're asking us to write the steady state curve. And here I have two fours because in another exercise I thought that it was this one. Okay. Well, I have here two fours. One that is x going from 1 to 5, and one that is the sleep going from 1% to 0%. So remember, the developed torque is based on a sleep. So here I have our R2, and what I'm doing is multiplying R2 by x. So in every change, I'm increasing R2 by 1 until I get R2 of 5. And for our sleep, I'm increasing it, I'm going down from 1 to 0%. So yeah, for a sleep of 1 to a sleep of 0. Um, and that's what I'm doing. Then I'm just plotting these values. And also I'm gonna plot what is the maximum torque for each curve, because we're gonna have 5 curves, each one with an R bigger and bigger. So we are gonna see how they change. So if you see here, we have a maximum torque that does not change. It's always 270 for all the curves. Our first curve is the curve of our exercise. Uh, so you can see here that if we increase the resistance, we get a developed torque. We get a starting torque that is bigger, and we get our maximum torque and a slip that is smaller, or a speed that is smaller. So this is a way of controlling the speed of the motor. But it's just that it's not convenient to be changing the actual resistance in a motor while it is running. Okay. Okay, now we have this exercise that is asking us for what is the maximum torque of this motor, our speed, this slip occur. Okay, so before in the previous video, we figured out uh, our maximum torque when we have our Thevenin equivalent. So here I have the snippet of the video where we have our how to calculate our V1 equivalent and R1 equivalent, and how to get R from the equivalent circuit. And we use the maximum power transfer theorem to get these formulas for our maximum slip. Okay, I didn't want to go easily. For our maximum slip, and then we plug this value into our formula for torque, and we got that our torque, our maximum slip is this value. Okay, so first, what is the maximum torque at this? So we need to get our equivalent values, and we need to get our value for Vm. So we know that Vm is gonna be our 460 volts over square root 3. And now for our equivalent, V1 equivalent. Well, since it is just a formula and we're giving out the values, I just plug it in MATLAB. Here I have a formula for calculate V1 equivalent. That is just V1. So it's just the formula. And for this, because we are in a steady state, we only want the magnitude. So I just return the magnitude. So this is gonna give us a magnitude of 2.789 and an angle of 0.0234. And I did the same. I created in MATLAB a function for calculating our R1 equivalent plus our J X1 equivalent, and we got 0.59 plus J 10 1.7052. So I'm not doing it because it is just plugging values. Okay, so if we plug the values, again I created a function in MATLAB to get our maximum slip, that is just using the formula that we derived before, and we're gonna get a maximum slip of 2.014. So now if we have a maximum slip, a synchronous slip of 120 times the frequency over the number of poles is equal to 120 times the frequency over number of poles, that's equals to 1800. We have done this one many times before too. So if we turn this into 2 pi over 60, we get 60 pi. And we need this for our synchronous. So that we are going to plug here for our what is our value of maximum torque. And when we plug these values into our formula, we get that 230.8 newtons per meter. So it is really just because we are giving almost all the values, we only needed to figure out what was our synchronous speed, but not in RPM. And here in MATLAB, we just calculate, we have a formula for TD max. When we have our synchronous, we have our V1 equivalent, R1 equivalent, X2 equivalent, and we just calculate it as the formula that we have. So just plug in the values. Now for second, what is the starting torque of the motor for a second? So starting torque, if we go back a little bit, not back, if we go into our formula, we know that when we started here, our S was, this is the percentage of speed, and this is our S. So when our S was 1 is when we have our starting torque. So again, it's just plug in the values when we have our formula for the torque. V1 equivalent square, C square over S1 equivalent plus X2 square plus R1 equivalent plus R2 over S square times R2 over S. So we just make this one, so we are only going to have R2. So RT is going to be 106. Again, I have the formula, so I just need to change the slip. For our tier 1, they are asking us to multiply R2 by 2. So what is the, we will double the resistance, what is the new starting torque of the motor? And what is our rotor speed? So if we go here, yes. So if we just plug the new values, we just plug the new values, we're gonna have a rotor speed of 10.75 RPM and our developed torque of 174 newtons. Okay, so we can see that it's like what we do here with this exercise, where we keep increasing our R, and our maximum torque does not change, because in the formula R, in our formula, yes, in our formula for maximum torque, R2 only change our slip. So in our formula for our maximum torque, we don't have R2, so it doesn't change. Okay, I know this exercise wasn't much, but this was just, now that we have developed all the formulas, it's just plugging the values.